part of the course, which is almost like another course. I used to do everything I did so far more slowly, and it would take me a few more weeks. And somehow we got by really quickly. Maybe you guys are really good students, or it went by very fast. So I'm starting another chapter, which is chapter of the course, which is all from a new book. And the book is called Introduction to Online Control, and it's online. It's on archive. You guys can download it. Not out yet in print, but it will be, I think, in a few weeks. And in any case, I'm still updating the book. There will probably be new chapters uploaded in the next few weeks on archive. So I'm really excited about this topic. This is a part of the course or part of the material that I've taught less, and it's more new. Much of it are very recent research results. And therefore, I will ask questions that some of them are research questions, even theoretical research questions. You might yourself ask me questions that are, the answer to them is unknown, because I'm going to talk about a new theory. And I think this theory is particularly relevant to the AI of generative models that we're seeing today. And indeed, much of the results I'll talk have to do with it, or much of the examples. And you can, of course, ask me during the class, how do things fit in? How do I think of different structures or different constructions? And I will try to answer to the best of my ability. But again, this part of the course is more researchy and new. And it's not like calculus that everything was done in the 17th century. Okay, this is new stuff. So there are many, which I think is exciting. That's a nice, exciting thing. And I think I've had students, like just David now reminded me of the alumni called Evan Dogariu, who is now, he worked with me for a couple of years when he was an undergrad, like many of you guys now in the audience. And he did really well. He has some really exciting research results. Some of them I'll talk about in the second part of this course. So today, and maybe you guys can all be like Evan Dogariu. I hope so. I'm sure some of you can reach that level of success. So today I'm going to talk about learning and control in dynamical systems. It's new. It's very different. It's going to be an introductory class to this material, and I'm not going to do a lot of proofs, maybe one proof if I get to it, but it's going to be more definitions and thinking about the definitions and thinking about the model and thinking about the problems. So it's more of a, if you will, philosophy kind of class. We've had maybe one of these right in the past. So philosophy 101 for today. What do we mean by learning in dynamical systems, learning and control of dynamical systems? And I will start by telling you a bit of history. And the history goes back to the 17th century. Control is a discipline in engineering and sciences that has to do with the manipulation of physical devices to get some desired behavior. Now, this predates computers, okay? And you might wonder, why am I talking to you about things, steam engine and stuff like that, when we have AI? I think it's very relevant. I think the mathematics for it are far from being well understood. Still a lot of inventions and discoveries being made, and I will try to show you how relevant it is to today's AI. Nevertheless, the history goes way back. So 17th century, steam engine was invented. I don't know all of the workings of it, but James Watt, who was maybe the main innovator in that engine, which of course is the main invention that started the Industrial Revolution. One of the main devices he invented is called a centrifugal governor. So governor, not like a governor of a state, it governs some behavior. And the idea is, I can't really draw it here, but it's in my book, a drawing of it. So, but let me kind of draw a schematic. The schematic is we have the steam engine. You need the steam engine, the way it works is you boil water in a boiler, then it generates steam, then the steam goes through all sorts of pipes and cause the wheel to turn, right? Cause some mechanical movement. So the heat is transformed to some mechanical movement. Now, how much heat? You need to heat up the boiler And the way you would heat up the boiler, maybe it's on a train. You need to feed it with coal to burn. So maybe it will get too hot, the pistons start running very, very fast. You need to wait a bit for some of it to burn out. Then it cools down, the wheels don't turn as fast, so you need to put in more coal. And someone needs to watch it, right? Or ideally, you need someone to make sure it's running at the same speed all the time. So he invented the following. That really made a huge difference. There is some kind of I don't know how to say this in English. It's a ball connected to a stick. It's like a pendulum, but it's not really a pendulum. It turns around. It spins. Okay? So this thing spins around because it's connected to the engine. So this is connected to the engine. And the faster the engine moves, this spins faster and faster and faster. Okay? This is connected to a shaft. And when it spins very, very fast, the shaft opens, which causes some lever to turn, closing the entrance of coal to the boiler. So you can think of this kind of lifts and decreases the lever. If this goes very, very fast, by centrifugal force, it goes up, and it brings the lever down, which causes less coal to go into the boiler, which causes this thing now to cool. If it cools, it spins slower, so this goes down, it causes this lever to go up, and more coal goes into the engine. Is it clear what I said, the example? Yeah? It's a mechanical device. There is no intelligence in it at all. There is nothing computational here. But it's a good example of a physical system that is controlled by physical properties, and it causes a desired functionality. In this case, it regulates the workings, the temperature of the boiler, and therefore the working of the engine. Otherwise, it would keep on go up and down, faster and slower. There will be no regularity at all in the operation of the engine. You need something to control it. Does it make sense? I hope I illustrated it okay. You can watch videos of it. If I had slides, I would show videos of it. If you go to any museum, I was never interested in these museums of the 16th century, but you see all the steam engines. But now I am. I say, oh, you can actually see this thing, this device. It's illustrated there, and this was invented by Watt in 1700s sometime, late 1700s. And it's basically a great example of some automated control mechanism. In this case, pretty ingenious. There is nothing, no one operates. It's totally automatic and self-regulating. It's self-regulating the operation of the engine. More generally, what goes on here? You can think of many other examples of physical apparatus that we would like to control. This is a steam engine. Okay, so this is a steam engine. But there are many other examples. A few examples that I like to give. One of them is called the medical ventilator. This is how I got interested in it. I'll explain to you what it is and why it's relevant to what I'm teaching. A medical ventilator is a device that is used by physicians to introduce artificial breathing for a patient. The patient is sedated, they cannot breathe, because either they have some operation, or they have COVID, or it's a prenatal baby or something. They cannot breathe on their own. So this device basically pumps air into the lungs of the patient. The patient cannot do it by its own. And then it needs to simulate healthy breathing. So it needs to simulate, if you look at the air, this is air pressure. Inside the lung, and this is time. Then you want something like this. And this is some capacity of the lung, and you want the air to go in and out and in and out, something like that. That's what you want to happen in terms of the pressure of the patient's lungs. So clearly, you need a method of injecting the air into the lungs of the patient by some tubes and so on. So there is an air source. There's all the apparatus that connects the lungs to the air source. But you also need a control method to make sure that you're constantly measuring how much pressure there is. You don't want to put too much air. And you also want to make sure that you don't have too little, that it doesn't go idle and goes up and down. And if the patient is coughing or whatever and there's some obstruction, you want to take notice of that and make sure everything is operating well. Okay? Example understood? So we got interested in it, my lab and me got interested in it during COVID. And at the time we're saying, how can we regulate? Let's look at the control problem here. I know nothing about anything medical. But I do know something about learning and reinforcement learning and control. And maybe there's something we can do to help. At the time there was COVID, a lot of people were connected to these ventilators. It turns out it's a very important device. So every time, I hope none of you go into an operation, but I did, for example, then you need to be connected to this device. They cannot operate on you without this device. It's a very critical device in current, and used all over the place, in current medicine. And the way it works, there is either a person all the time, it used to be just a person manually putting air into the lungs of the person by switching it in and out. Or now there are medical ventilators that are automatic, but they have all sorts of issues. For example, they cannot detect if this is too steep, maybe it goes up like this, maybe there is an obstruction. So you want some more intelligent behavior and potentially help people in their medical condition if you have a better control method. So this was the motivation. And what we looked at the time were neural networks that were trained to induce this behavior according to the specification of the physician. So the physician would say, I want this kind of behavior of the pressure in a long time, and then we trained the neural network to simulate this kind of behavior. This was our work at the time of COVID. So it's a nice story is that it was released open source, and it's actually this technique, this method is now in use. So it was released to the public by some actually commercial producers, and it's used in hospitals. So maybe there are some people who have a better life because of this, are interested in it. I'm very happy about that. So that's another example. Let's see. Oh, okay. One more. Let me give you one more example of a control of a dynamical system. So I'm going to use another medical example. So this is called the SIR model in epidemiology. I don't know if this is the correct way to spell it. So by that I mean, probably I'm making some mistake. This is the study of disease, spread of disease. Epidemiology. Let me write the correct. Epidemiology, something like that, right? MEG. I'll make it illegible, so it's, you know what I mean. I mean spread of disease. So there is a model of how diseases are spread in society, and it's a very important model because you might want to intervene. And the way you intervene is in a non-trivial way. For example, during the spread of COVID, some people, so SIRS stands for susceptible, this is infected, this is recovered, and they all sum up to 1 because that's the population in the group that you're testing. And what is your control variable, or what do you affect? Well, you affect maybe quarantine. How many people are under quarantine? Now, you can put everyone under quarantine, but that's not an optimal thing to do because no one develops any immunity, and it can spread out at any moment, and then you can overwhelm, or people have a low quality of life, all sorts of other issues, right? Children develop social anxiety and so on. So you wanna quarantine, but in a way. And what is the way? If you don't quarantine at all, maybe you're going to have a spike in how many people get sick, and that overwhelms the hospital. That's also a bad thing. So you see that you want to strike a balance between how many people are infected and can get treatment and recover versus how many people are in quarantine. So that's kind of the idea. If you do nothing, usually what happens is the number of people who are infected will go up like this, something like that. Okay? And this spike here, I will show you the equations that come out of the equations. This can overwhelm the hospital. Maybe the hospital capacity is over here. So you want to quarantine in a way that is always under this line, maybe something like this. Maybe that's a better graph for society than this. So there are all these considerations for the decision makers that they can take into account to induce better public safety. Okay, I can write here a million more examples. People heard about controlling rockets when you want to put satellite in space and so on. So all of these are examples of physical devices that have a certain behavior coming from physics that we understand well, from physical equations. And then there is a question of how do we control these physical devices or systems to a desired behavior. What I'll do next, I'll write down the equations for the model, for the mathematical model, and then discuss the problems that we want to attack. Okay? Questions? Okay. So formalization. The main object of study here is called the dynamical system. A dynamical system can be a steam engine or a medical ventilator or a population dynamics in terms of the SIR epidemiology model, or a rocket, or the most interesting one is going to be an LLM or the human brain. To me, that's the most interesting one. So how do I represent that? Well, I have 3 or 4 objects. So xt is going to be the state at time t. Then I have ut is going to be the input or control. I have wt, that's going to be some noise. And yt is the observation. And the equations that govern a dynamical system, as I said, the theory of it goes back centuries. Usually, what people talked about for dynamical systems are differential equations. Now, differential equations, in my opinion, are not suitable for this particular course, because I'm not an expert on that, so I'm not great in differential equations. But I also think there are other objective reasons for that. The reason is that when we apply algorithms, we usually do it on a computer, and the computer is discrete time, and we are dealing with discrete time algorithms. So it's very inherent for me to have discrete time equations. Second of all, many phenomena that are visible in discrete time are not visible in continuous time. And this usually has to do with rates of convergence. This is true even for mathematical optimization, but also true for dynamical systems. So you get a more refined view of the rates of convergence and finite time behavior as opposed to infinite time for differential equations. So the finite time dynamical system has the following behavior. I have xt plus 1. The state changes according to some dynamics function that is applied to the state input and noise at time t. Yeah?
Let's go back. Or just say 1 is the...
Nope.
No?
Nope. Yeah. And then my observation at time t plus 1 is some function applied to the state. So f is called dynamics function, and g is usually called observation function. For example, let's show an example of such dynamics. So when we have a box on wheels or car, let's say, on a road, and a force applied to it. Okay, so the force is U. force at time t. Then xt is the state of the car, and it's going to be composed of two coordinates, position and velocity. Okay. So, what are the dynamics as a function of the force? This comes from Newtonian mechanics. And I can write the following dynamics. So xt plus 1 is xt times the matrix, which is 1, delta, 1, 0, xt, plus 1, 0, ut, sorry, 0, 1 ut. So what goes on here? Delta, if this is the time resolution. So what I wrote here is that the position of the car at time t plus 1, the first coordinate is the position, is whatever position it was in the time t, plus time times the velocity, right? This is Newton's law. Yeah, Newton's law of motion. And then what is the velocity at time t plus 1? So that is going to be the velocity at the time t, plus the force at time t. So this, maybe you want force divided by, this can be like 1 over m. So m is the mass. And then if they measure the force by Newton, then F equals ma means that the velocity, so I can kind of add to it, the acceleration is force divided by mass, and I add to the velocity time t plus 1, velocity time t plus acceleration. Yeah? Yeah, delta. Delta divided by mass, yeah. Yeah. Correct. So this is a dynamical system. It's called the double integrator usually. It's called double integrator. And the reason it's called the double integrator is because I integrate the force into the velocity and the velocity into the position. Okay, so twice. And this dynamical system represents how a car moves under force. Okay? Any questions? Yeah? No. You know what? Yeah. Let's make it always. For this course, it can only be time invariant. It doesn't have to be linear. It can be nonlinear. You're right that in general, I can make this, if you want, I can make this to be dependent on time, and then it kind of is a more sophisticated model. But for the rest of the discussion in this course, I'm going to always stick to time in, well, I might have time varying if I talk about linear systems. For nonlinear time varying, it's a very sophisticated model. And even for simpler models, many questions remain unsolved. So I'm going to stick to the simplest possible models. Yeah. But it's true. You can have dynamics that change over time. This is definitely possible. Any other questions? Yeah. Time varying?
Like, yeah, like would you say that most practical?
Okay, this is what I think. I mean, in the conjectured part of the course, okay, nothing here is known, in my opinion. And I've talked to the leading experts in control worldwide. So in my opinion, this is a very fine model. F and T, no time varying. And F and G are nonlinear, Lipschitz, and stationary. Okay? Let me give you an example. So example 2. LLM. Okay, so I have XT. This can be the context, all weights of a neural net, weights of the neural net, KV cache, all other parameters of a certain neural net. Then UT can be a token in RD model. So this means the word embedding model dimension. And WT may be 0, no noise. And then I have XT plus 1 is F of XT UT. I'm now doing some abuse of notation. I'm W0. I'm not putting it in. If you want to add it, you can. So what happens when I apply dynamics function when I add a token to the neural net? Well, it depends if I'm doing pre-training, for example. I'm doing a back propagation, okay, over some loss, cross entropy loss through the system, and I get another state. So the weights are updated. If I'm doing generation, the KV cache maybe is updated, but the weights are not updated. So there's a bit of a different behavior if I'm doing pre-training or generation. And then what is YT? So YT plus 1, G of XT plus 1. What is this? So some forward pass, right? Yeah, you're saying? Yeah, forward pass, so I should have let you say. So there's a forward pass through the network, and then a token is output. So there's going to be also a token produced from the state of the whole machine at time t. This is a very new way of looking at it that I'm describing to you now. Yeah, question? David?
Yeah, why wouldn't the token just be part of it?
Some tokens are part of the context, but usually the model stores them in some kind of representation, which is not necessarily the token, the word embedding representation. So it stores KV cache, it depends on the machine. Or it's a Mamba model or an SSM, then it stores some other state information, but it doesn't have an interpretation which is naturally a token. It could be. It could store the past 1,000 tokens in memory. That's fine too. I allow that. But it can be more general. Questions? Yeah, you're all okay with it? Interesting. Okay. So, well, now the question is, what's my goal? I described a mathematical model of a dynamical system, and I showed you some equations. Okay, it can apply to a car with force applied to it. You can imagine I can write an airplane here, right, with all sorts of forces and wings and whatever, and properties and weight. I can do that too. It's in the book. I can have a more sophisticated dynamical system. I have the steam engine. I have all these other medical ventilator, and an LLM maybe. So it's a very general mathematical model. But what do I want to do with this mathematical model? So here, I would characterize that there are two main different problems that I might want to pursue. The first is called learning. Learning in dynamical systems. This is goal number 1. Chronologically, it's actually the newer of the two. Definitely the LLM problem, modeling it this way, is much more new. very recent. What do I mean by learning? So you might think that there exists a dynamical system, starting state is some x0, and it starts to evolve. It evolves, and I see y1, y2, yt. And I would like to predict yt plus 1 hat. Maybe I want to predict yt plus 1 hat. And what makes sense here, I believe, or the most interesting case are when I don't know the dynamics function and I don't know x0. Because if I know x0 and I know the dynamics and I know the inputs, then I can maybe compute it, right? I can compute what is xt plus 1, what is xt plus 2, so on. But I don't know, because it's in my brain or the LLM or the whatever device. So I see all these observations, and I want to predict the next observation. So this means that maybe I want to minimize summation t from 1 to big T, yt minus yt hat squared, or some other loss, maybe cross entropy loss, or any other loss that you may think of, which is convex. Maybe I want to drive that. It would be nice if the average of this goes to 0 as t goes to infinity. So x0 and f are unknown. Maybe u1 to t are observed. So I also see u1 and ut maybe. Or maybe they're equal to y1 and yt. In the case of language, they're equal to, because whatever tokens I spit out, usually they're passed back into the machine for the next prediction. There could be noise, it could be noise-free, but f is unknown and x0 is unknown. I maintain that's kind of a very reasonable setting, that these things are unknown. And then I say that this dynamics is learnable if and only if for every x0, let's call this error t. So error t goes to 0 as t goes to infinity. So surprisingly, this is a relatively recent definition. It's not an old definition. It's different from the other learning definitions that we have seen. Yeah? Oh, okay. So let's go through the rules of the game again. This is very similar to online learning, okay? So the protocol, the learning protocol is like this. I'm not sure if this is in the book, by the way. I think it is, but I'm not sure. If not, then I'm writing it here. So, but it makes sense. Given what we have all studied this far, this makes sense, I believe. So the protocol is like this. You see y1 up to yt, and u1 up to ut. Then you predict yt plus 1 hat. Then you see yt plus 1 and suffer loss. And this happens again. Then it happens again. Yes. Ut plus, yeah, correct. So you see one more UTs as opposed to the Ys. Yes, you're right. Yeah, makes sense. Does this make sense? Questions? So let me ask you, how is this different from online learning? Yeah,
Wait, I have a question.
please.
So I thought that you use YT plus 1.
In LLM sense? Yeah,
Right?
yeah.
YT plus 1 is the token. Also the ground.
Well, in LLM there is no use. There is no use at all.
That's why I was confused about the because the LLM example has UT as the token.
Sure. So it could be either that, well, I guess for LLM, let's see. There is a difference between pre-training and generation. So pre-training, you see the U's and you suffer the Y's. Does it make sense? So you see another, you predict a YT plus 1, then you see the real YT plus 1, which is actually U, the kind of the next U maybe, or something like that. And then,
Right. But you saw UT plus 1.
so let's say UT plus 1 is going to be 0.
Yeah,
Okay.
that's what.
Okay, so it's 0, and then yeah. You don't have to kind of, there is more information here that I need to make use of. But we can write it, let's write it for LLM, what makes sense, okay? So for an LLM, the way I would write it is that I predict YT plus 1, then I see YT plus 1, and I suffer this loss, okay? And, okay, there are no use. There are not going to be any use. For the LLM, there are not going to be any use, okay? You can think of them as an extra hint, maybe another extra information, or you can add more complexity to the picture. But nothing. I just predict the next token, then I see it. Then I predict another token, then I see it, and so on. That's what happens in pre-training. In generation, I predict the next token. I put that as the ground truth and continue. And I don't get any loss. My loss maybe is only at the end.
Maybe
Potentially, yeah. Or maybe there can be the prompt, if you want. Prompt to begin with, just you one, there's no other use. Yeah? Yeah. You can model distillation this way, I agree, you can. So you can model distillation, pre-training, all of these things you can model with this generic problem, right? People are with me? You agree? Well, I will ask you then my question that I wanted to ask you. How is this different from online learning? Yeah, Elijah.
Online learning, you had FT, and FT could be arbitrary each round, that's your loss. You chose the input to this loss function every round. This, you have a set dynamics function and a set state. And the way that the state evolves is already predetermined. You're choosing UT, which is impacting the way that the state evolves, but it's not fully arbitrary.
Kind of. So there is something in the notation that I wrote that confuses maybe confused you, maybe confused more of you. And that is the choice of function f. So f dynamics here is fixed. In the online convex optimization, it has a loss function. Okay? The loss function, the role of the loss function is going to be captured by this L here. That was going to be, this can be the loss function in online convex optimization. It is unknown ahead of time. It can be arbitrary, adversarial, okay, even for dynamic learning. In that sense, I can model this as online learning, but there is something more special happening here. Yeah, Colin? Yeah. I agree to that. Why do you say I agree? That's correct. Why?
Well, one, we're also given command of the function. Like before in online learning, the command
Right.
just have enough.
Right.
Now we're getting
Right.
that.
Yeah.
And then also the function is also
Yeah.
squares.
I agree with what Colin said. Let me recap. Colin is saying the following. There are more things going under the hood here that I didn't assume in online learning. Online learning, there's just a sequence of online adversarial loss functions. That's it. And I'm making predictions, then the loss functions come about, and I measure regret compared to the best fixed point in hindsight. Okay. Here, there are all these X and states and evolutions under the hood that I didn't assume in online learning. It could be anything. For example, I could model SSM in the online learning world, predict the next token. Oh, you were wrong, or you're right. Okay, there's no, without assuming anything in the background. It fits into online convex optimization. You can then ask, okay, what do I compete against? Obviously, I don't want to compete against the best fixed token. In hindsight, that doesn't make any sense. I want to compete against the best fixed predictive model in some class, which I could try to learn, maybe neural network or transformer or something like that. But this is more special because I'm assuming more things are happening in the background that generate the loss. But you can see in the examples that come from the physical world, it makes total sense that these things actually exist. If we believe that reality is real, then they do exist. There is a LLM predicting, there is a brain predicting the tokens that are written in text, and later I train the LLM on. And there is a real car that I want to predict where its position is going to be in the next iteration. Okay? Yes?
Definition of what training modifier.
Yeah. That's a good point. So what I want it to happen, I want this to go to 0. This somehow assumes no noise at all. Because if there is an inherent background noise, maybe you can't make it go to 0. You're going to have the variance of the noise coming in. So this assumes noise-free. This is noise-free. You can make, this is a very good point, you can make noise-robust version that say, I want to approach the average mean square error, or you can make comparative statements, I want to compete with some predictor class, and so forth, which we're going to do later. But for now, let me write down just this definition. So let me make a small analogy to the Kepler model of movement of the stars in our solar system. You might think of a model where you're trying to predict where is Saturn going to be next. Okay, think of this problem. You have an observation from a telescope. Where is Saturn going to be? Oh, it's here. Oh, it's there. You know, you can try to predict where it's going to be. And you can use various models to try to predict neural networks or various other machinery to try to predict where it's going to be next. But what did Kepler do? And Copernicus and all the other scientists of the past, they basically assumed a model in which there are stars in various locations. They have gravitational power between them, and that governs the laws of what's going to happen. And this gives you an ability to predict not only next token prediction, but many iterations into the future, what's going to happen. There is an underlying truth behind it that they try to recover. Okay? So that would be the analogy of what I'm saying here in this model. There is the reality behind the observations that we could make use of, we could try to recover. This is called system identification. We can try to not care about it, just having this metric go to 0. That's what I kind of advocate for, next token prediction. But definitely there's a lot of thought you can put into it and philosophize what is the correct notion here. And I don't think anyone knows at this point. I really don't. But I also think this is the correct way to move forward when we're talking about trying to describe intelligence and why does predicting the next token give rise to intelligent behavior. It does come from learning some underlying model. Okay. Questions? So this was problem 1, which actually is the one we're studying more these days. But before we studied that, we studied a different problem. Historically, this is also true, which sounds like a much harder problem, and that's the problem of control in dynamical systems. So in the problem of learning, we see the y's, we see the u's, we're trying to predict the y hats and make them close to the real observation. And you all didn't argue with me so much that I told you this is a very interesting, important problem, because you all understand how LLMs are pre-trained. That is the reason. That there is a lot of reception in the audience, I feel, because of that. Of course it's important. It's how we do pre-training for LLMs. Okay. That's my interpretation from your silence, relative silence, okay? But historically speaking, this was the less interesting or got less attention than the problem of control in dynamical systems. In control, we actually want to solve for u1 to ut such that to achieve some functionality. How can I capture that mathematically? So let C1 to Ct be loss functions. And what I'd like to do is to minimize over u1 up to ut summation t from 1 to big T, c little t, y little t, and then u little t. So if I were to call it f little f, this would be kind of looks like online convex optimization problem, but I'm solving for an actual, not a prediction, a control, something that goes into the dynamics and affects the state of the system in the next iteration. So very, very important is wise, right? So this minimization is such that I have xt plus 1 is f of xt, ut, wt, and yt plus 1 is g of xt plus 1. So this is always in the background. There is something like this happening in the background when I solve for the u's as opposed to online convex optimization. There is always something happening that I'm trying to solve for. What I do, the actions I take, they affect the state of the next iteration. In learning, they don't affect nothing. I'm just trying to predict. I don't have any effect of what's going to happen. So let me show you what happens for the double integrator example. What would be a functionality that I want to achieve? So for example, Ct can be the same Ct always. Maybe it's going to be xt minus some x star 0 squared plus ut squared. So this means, what does this mean? Who can tell me? Yeah.
You want to get to a particular location,
Mhm.
and I guess not accelerate too much.
Zero velocity, stay there. Yeah, yeah. And I want to do it while minimizing force, exactly. So I want to compute the minimal force that I can apply to the car to make sure it arrives to the x star and then it stays there. Okay? Yeah, makes sense? So you can compute that actually. You can try to compute that for the car and you will see what comes out. I think it's like a uniform cost. You kind of spread it out because there is a square here. You don't want to assign a huge force and then it's going to go all the way and then kind of a huge force and make it stick there. You're better off spreading it 1 over t or something uniformly across time. Then it gets to the final position. Then you say, okay, now make sure the force back a little bit so it stays there. Okay? Make sense? Where is Anthony, the physics guy? He's not here? Tell me. Yeah, question? Yeah. So I think what I want to have is maybe some friction. I forget how to model it. Probably there is a way to model it too. So maybe, I think maybe it means that there is a the velocity decreases by a little bit. Okay, so here, yeah, the velocity. So maybe there is some minus epsilon here. So velocity, but then if it's negative, you want it to go positive. So it's some kind of like, it's going to be time varying. This is going to be time varying. So 1 plus epsilon, 1 minus epsilon. So kind of shrink the velocity, depending on if the velocity is positive or negative. And that will give you some friction. And I think this will resolve whatever you said about you have to put some force all the time. You can't have no force because you're going to basically slow down to a halt. Yeah?
So I have like a short question. This seems like a very nice model when your state is in some way like inherently what you're trying to transform your goal. But if you're doing robotics, for example, you
Yeah.
have a robot and you have, you know, a state of the robot, but what
Yeah.
you really care about is the way that the robot interacts with its environment. So I
Right.
want a robot to go pick an apple and place it in a basket.
Yeah.
How do you get this model to fit within that paradigm? What I really care about is
Yeah.
the way that my system causes change in the environment,
Right.
which then influences.
Right, right. So what you're describing, by the way, control is the de facto standard for mathematical modeling of robotics. There is nothing else we know. Nothing. I mean, there is reinforcement learning, which is equivalent to control. I will talk about that too. But basically, same model. It's the same model. And the way, what you're describing is reward function design, the hardest of reward function design. Because the reward functions capture instantaneous reward over my action and over the state of the world. And how do I reward shape? How do I shape the rewards in such a way to achieve functionality which is more complex? That's not a trivial thing to do. It's indeed one of the difficulties in robotics. And actually robotics, as many of you might know, is not a solved domain. Far from it, okay? We know we're pretty behind, much, much more than any other areas of AI. There's been a lot of progress recently because of the AI that allows for efficient planning. You can ask the LLM, please design a reward sequence that will get me the apple into the box. Okay? But otherwise, it's pretty much an unsolved problem. Lian, my grad student, might know something about it, right? Am I right what I'm saying? Okay, okay. Do they have some other way of doing? I mean, I don't know. There is another way of doing reward shaping, right? I mean, you can ask the LLM maybe to create a set of rewards, but I don't know if there is anything else, or hand design, or. And indeed, much of the problem comes from that. Like if you're solving an Atari game by observation, so your input is a sequence of images describing the Atari game, and you all heard about the Atari, right? Atari Go, whatever it's called, Alpha Atari, I don't know, the DeepMind Atari solver. So there are rewards. Every time you pick a gold coin, you get a reward. Every time you kill the monster, you get another reward. But now, how on earth are you going to shape the rewards in such a way that will elicit the correct policy, the correct behavior? That's why it's a hard problem. We don't know how to do that. Okay? But nevertheless, it is possible to do. So it's possible to do by some mechanized ways that we'll talk about. Does it make sense? So I don't really know how to shape the reward in such a way to elicit very efficient planning in terms of the controller. No one knows how to do that. We know how to do very special cases, which I'll discuss. More questions? That was a good question. Yeah?
For the vector field, for UT, why is 0 not delta square over 2?
You're asking here?
Yes. Why is not delta square over 2?
Sure, delta square over 2n, yeah.
No, it's the 0.
This one? No. I don't agree. This is just a well, okay. The position is not affected by the force directly. It's through the velocity. Okay? So that's why it's 0. So this is the force. The force affects the velocity through the first differential. And then the next iteration is going to affect this is the time integration. This is a discrete differential equation. If I were to continuous differential equation, maybe you'll see it more precisely, I think. Okay. Yeah.
So iteration here, updating the velocity, right?
Yeah.
By force.
Yeah.
And then you're using a forward velocity.
Yeah,
update the
that's right.
So there's a
That's
lag,
right.
right?
There is a lag, yeah. But you can think of this lag going to 0 and then thinking, yeah, it's a model. I mean, maybe you can have a more accurate model that what you say also affects the position immediately by the second differential and so on. But this is like a one differential. It's the first differential equation. So it's a differential equation of the first order. There is no second differentials here. If there was a second differential, I would have xt minus 2. So it's discrete. It's a discrete differential equation, okay? If I had xt minus 2, maybe then there will be a square coming in through the force to the position and so on. Yeah? You had Kia, you had something? No? Anyone else? Yeah? Oh, it's very problem dependent. So the question is how much knowledge you have over F and G. Very problem dependent. In the most general case, you don't know F, you don't know G, you see the sequence of Y's, and you want to minimize cost. This is the case, for example, in Atari. You have no idea what the dynamics are. There could be a Pac-Man running around there. You have no idea what governs it. By that, I mean the monsters, you know, the Pac-Man monsters, they're running around all over the screen. Then you have the observation. It's some complicated, depending on where you put the camera, and then the camera might have all sorts of blackout, and God knows what happens there. So it's not clear how the camera projects onto the state. The state may be of the Pac-Man. If you're watching a Pac-Man game, where is the position of the Pac-Man? Where are all the monsters? Where are all the fruit? And the dots? And the maze walls or whatever. It's a complicated thing. It's not clear you even want to describe that yourself. You want an automated method that will automatically get you the best possible reward from observations. That, I think, is the real interesting problem of control or reinforcement learning. Well, yeah. Okay, you're asking a good question. Now, I'm just in the first lecture of a course that's not even dedicated to this topic, and it's about, you're asking me which variant of controller RL I should talk about. There are like courses for every particular variant that you're talking about, okay? There are courses here in MAE about known F, which is linear, and you want to solve for the best linear controller. That's one course, okay, undergrad course, which I'll probably do next week. But then but basically you want to do, there are many interesting cases. Linear is interesting. This is a linear system, okay? You can model linear systems by taking the Jacobian of a nonlinear system if it's a continuous smooth function. And it's a very powerful paradigm, linear control. There are interesting algorithms. There's a lot to say about it. And everything is known from the physics. So I have a physician, Anthony, he will tell me all the different parameters there, and I can design a matrix and solve. That's an interesting problem. Then there is a problem of learning in dynamical systems. I don't think there's any course that does that. That's a very new topic, and I'll talk about that. Then you can control nonlinear dynamics. There's no solution to that at all. Unknown, no solution. No one knows anything about it. So, yeah, there's a lot to, I could write here on the board, it'd just be a waste of time. What are the different variants? It's better if I say that. So the variants are known dynamics, unknown. Known observation, unknown. Linear, nonlinear. Known state, unknown state. Maybe the known state is, usually you don't know the state. So in the brain LLM example, I'm trying to predict the next word I'm going to say. I have no idea what are the weights, what are the conv cache, and all of these things. I don't know. I'm trying to predict it. Okay? Yeah, so there are numerous variants, and therefore I'm not going to enumerate all of them. I'm going to keep it open-ended for now, and we're going to attack it from the way I do it in this course. We're going to reason about what can we even hope to do in the simplest case and build up from there. And I hope you will see we can do pretty surprising things, The most recent state of the art is we can learn in nonlinear dynamical systems, provably, efficient algorithm. It's a very recent advancement. It's very exciting, and it's very recent. It's novel. Yeah, Jerry? Hmm. Yeah, you're already ahead. You're thinking about lower bounds for the problem. You're right. We can say something about that. Maybe I'll say something in this lecture. We're kind of running tight on time. But let me just wrap up the formalization. Lian, you have something? Oh, okay. Any other questions? Okay, let me define then the goal of control, okay? So I want to minimize sum of costs that's written here. Now, someone asked me, what about noise? Noise is very important, of course, and I can treat it as a stochastic random variable, in which case maybe I want to do, it's called optimal control, or reinforcement learning. In this problem, we try to minimize U1, UT, expectation under noise W1 to WT, summation T from 1 to T, CT, YT, UT. So we're trying to minimize costs under expected noise. You assume it's a random variable. Then some people say, okay, this is too optimistic. It only captures stochastic dynamics. This is only possible under certain situations. Maybe you want to solve robust control. Where we try to minimize U1 to UT, maximum W1 to WT in some constraint set K, summation T, CT. So in robust control, you try to take the worst case possible noise rather than just expected noise. And then most relevant to this course is something more new. It's called online control. And in online control, you don't have this minimum in the beginning because things are not defined ahead of time, just like our regret setting. So we're trying to iteratively choose U1 up to UT such that to minimize summation CT versus the minimum pi in hindsight, summation CT. Now this is more of a regret type metric. I'll talk about this much more, but just now as a kind of an introduction, what I will try to do here, I don't know the noise ahead of time, but I can keep on choosing a control UT and compete with the best controller from a class. What is pi? So pi is a policy which is a mapping from state or observation to action from a certain class. So just like in online convex optimization, it's very hard to compete with all possible controls in an online way. This is impossible to do in general. You have to restrict yourself somehow. You will get a stronger guarantee, stronger than robust or optimal. But you have to constrain yourself somehow, and the way we constrain ourselves is by restricting the policy class that we choose from. Yeah.
And just to be clear, the policy is a mapping of a single state to the actions, not a history state?
Yeah, usually the formulation that I gave is Markovian. So the state depends only on the last state, doesn't depend on things before that. So you don't need it. If it's a partial observation model, you have Y's, you might need many of them, not only one. Okay? But if you have the state full observation, it's called full observation, so that's another distinction, which I kind of didn't Back to the question here. You have linear, nonlinear, full observation, partial observation, known system, unknown system, million variants. Okay. So what I'd like to do next is following what Jerry asked. Talk a little bit about what can even be done. What can I even hope to do in full generality? What is the solution concept? So, okay, I try to minimize cost. That's one thing you can try to do. But even before that, there are important notions that I need to discuss that are easier than control. We need to understand them before talking about control. And just use the notion of a dynamical system. The first is called an equilibrium. What's an equilibrium in a dynamical system? So if I have, let's say I have this kind of like a terrain, and I throw a ball here, I put a ball here, that ball is gonna maybe go up, down, and so on. If it stays here at the bottom of the hill, this is an equilibrium. It doesn't move anymore. If I don't apply force to it, it doesn't move. So it's a point x such that x equals f of x, and zero noise, zero control. So this is, for example, also an equilibrium. Here, point here. If it can get stuck on the hill, and it will stay there if there is no noise. But this is not a very stable equilibrium, because if there is a wind or something, the ball is going to fall down. So we say stable equilibrium is x equals f of x 0, 0, such that for all x in some epsilon neighborhood, x tilde, small neighborhood of x, we have that the limit t goes to infinity, f to the t of x tilde is x. So if I apply the dynamics without control and without noise in some small neighborhood, it's going to go back to the x. That's what this means. So this is a stable equilibrium, and this is an unstable equilibrium over here. Yeah? Sorry? Yeah. Yeah, I'll do that for stability. So this notion is somehow relevant for dynamical systems, but less so for control. So I'm going to do that next. I'm going to define that for stability. So we say that f is stabilizable if for every x0 there exists some u1 up to, bless you, ut up to a big sequence of u's such that if I look at xt plus 1 is xt f of xt ut 0, let's say no noise, then xt approaches 0 as t goes to infinity. So I can approach the 0 state. It's called stabilizable. So that system over there is stabilizable. Okay, I can reach a, well, depending if that equilibrium is at 0 or not. But here is an example example. So for a matrix A whose norm is less than 1, 0, so it's stable from any x0 doing nothing. Because I can apply A and again and again and again, then I get A to the power t, and that approaches 0. So this is a stable dynamical system. Yeah?
Does my norm t still have to go to 0? I can apply something. You're wrong.
Not clear to me that, I mean, for now, no. There is a quantitative version of it, which I will say, but this is just an existential version. So there could be a dynamical system. It's not clear to me. I can show you one. For example, the Julia set system. So it's not clear that there's just like nothing you can do, and it's still not clear that you will be able to reach 0. Or it's not clear at all that there is any, it's an input independent system. So this doesn't affect the system at all. Okay, you have systems that don't affect it at all. Let's say for every u you put in, it doesn't matter. It doesn't affect the system at all, just the dynamical system. And then the other notion is we say f is controllable if for every x0 and x star, there exists a sequence of u1 up to u t and a t such that xt approaches x star. So not only I can get to xt, I can get to x star with some kind of sequence, some kind of inputs. For example, if I have a mechanical system of the car, I can make it with some unbounded force, I can make it reach anywhere I want. It's controllable. Yeah. Well, it has to be finite, I guess. For a finite one, like the car is controllable. But I guess what both you and the person over there, you and maybe someone before you, are concerned that there is no bounded here, right? These come from the classical literature, and they bother you because you took my course. So let me give you a definition that will, I hope, will be nicer to you. So the other, see, more precise here. Okay, so we say, here is kind of a stronger definition. So we say that f is gamma Bibo stabilizable, so bounded input, bounded output. If and only if the following happens. So for every x0 that's bounded by 1, and then for every noise sequence W1 up to WT, W's are also bounded by 1. So I'm kind of requiring the boundedness of everything. So there exists a policy, pi, such that the following is true. So xt plus 1 pi is f of xt pi, pi of xt, wt. I have the evolution of the dynamics. And for all t, this xt is bounded by gamma. So it remains bounded. And then we say that pi is gamma stabilizing. Okay, so this might be, who asked me? Colin. So this is kind of a more quantitative version. Okay, for every state, but not infinity, it's someplace, there is a sequence of actions that are described by the policy that makes sure that all the future states are also bounded and up to some noise. So the noise are also bounded. So everything is bounded, I remain bounded. That's a quantitative version of stabilizability. It doesn't have the whole infinity things happening, okay? Yep.
In this notion of stabilizability, the point that we care about is just any point, this gamma.
Yeah, that's right. That's right. So we're in some gamma ball. And as gamma goes to 0, you become stable in the previous sense. But you were right. All of you were right to be bothered by the previous definition. They don't have a quantitative finite bound to them. And I was also bound, bothered by it, which is why I wrote the book. Okay, but that's kind of I think you guys are right. It's not. These are kind of, you can allow all sorts of infinity happening, and it's not a nice definition. You want something quantitative. And finite bounds, regret bounds, we want things to converge. We want to know that after such and such iterations, we're guaranteed error is going to be something. All the nice properties we had so far. For optimization and learning, we want to apply that to control as well, and learning in dynamical systems. So I'm almost out of time. But people asked me, okay, what about this equilibrium? And Jerry asked me, can I use these bandit ideas and so on to do something or show some things are hard? So let me just conclude with some impossibility theorem that I will prove to you on Thursday. And the theorem says that determining if a dynamics F, which is a polynomial of degree 6, is stabilizable, is NP hard. So maybe that's a good starting point, kind of to showing you these things are very hard in general, okay? I have a dynamics, and it's even a polynomial of degree 6, it's not such a terrible degree. So just understanding whether it's stabilizable, forget more complicated things like controllability and efficient algorithm and all that. Just determining that is already NP hard. And that's kind of a good starting point for our investigation to understand what can be done and what cannot be done. And in fact, I will tell you, here is the dynamics. You can know it. I'm giving you the dynamics now. All you need to do is determine to me whether it's stabilizable or not. That's still NP hard. Known dynamics. Full observation. Okay? I don't have time to prove it. I'll do it Thursday. But any questions? All right, folks. See you Thursday.